Should I be connecting here?
Yeah, he will connect.
I got it. Yeah, sure.
This side or that side? Yeah. Is that the latest version? Yeah. So go down. Go. Let's. No? You want to put change? Yeah. Okay. Good morning again. So here in this session, I just want to give a very high-level overview of what is happening with the MVAPICH project, the latest status, our future roadmap. As many of you know, we are in an exciting phase. I mean, this year especially, in June, we crossed the 1 exaflop. For the last almost 10, 12 years, people were talking about exaflop, and now it is there, kind of things. And now people have started talking about the jetaflops. Okay, so that will be for the next 15 years. So as a community, we are in a very exciting phase. Now the question is, how do we really design software ecosystem for this, and especially from a high-performance MPI perspective? And this slide trying to show the challenges, like we almost like work on the programming models. I mean, there are MPI, PGAS, CUDA, OpenShift, Hadoop, Spark, TensorFlow, PyTorch, etc. And I call these these are like the supply side. There are many vendors here. I mean, they keep on coming up with better and better technologies over the years with features, but then the application people are sitting on the top, and they want the best performance and scalability. So how do you really bridge the gap? And of course, those applications typically use some middleware, could be an MPI layer or some other stack. And then the biggest challenge comes in designing its runtime. And that's what our group, or MVAPICH, has been working for the last 21 years. And you can do these kind of designs either in a layered manner, or you can also do co-design. So we explore both the directions. So in that broad context, if you ask the question MPI plus X, I mean, X can be anything starting from simple OpenMP, it could be CUDA, or it could be PGAS, OpenSMEM, any of those things. You will come up with this kind of a list. Okay, I'll not go over this, but these are kind of the traditional wish list. And for each of these directions, people want better solution with performance, scalability, fault tolerance, all those things in mind. And this is where, in that big landscape, MVAPICH project sits. So what we'll try to present here is like very briefly provide an overview of the MVAPICH project, if some of you are new. And then many of you would have seen, if you are on our mailing list, we made a lot of releases recently. I mean, these are like our internal deadlines. MUG is coming. So you have to make releases. So I'll go over some of these releases, what we have done. And then for each of the releases, I'll just show some sample numbers, the scalability. And then I'll say like what are the upcoming things, what we are working on. So this is the slide. You have been seeing that since yesterday. If those of you are new, we started almost day one of InfiniBand. When October 2000, InfiniBand was announced, we're the very first group in the world. I'm very happy to indicate that. We jumped in, we started working on that, closely worked with Mellanox that time. And we had our first open source version being demonstrated at Supercomputing 02, 20 years back. And people cannot imagine that time. I remember on the show floor, it was Baltimore, 8 nodes of InfiniBand. It was hard to really keep it running, okay? And people were amazed. I mean, the InfiniBand has come, it is running on an 8 node. That was a big news. Now, of course, it's 8,000, 80,000. You go into those thousands. Those are the kind of newses. But over the years, we started with the InfiniBand, but now we have gone into all different interconnects. As you can see, like Omnipath, Rocky, AWS EFA, Rockport, Slingshot 10 and 11, Broadcom, kernel-less network. So any network is available these days for HPC, we actually support that. And of course, we have been progressing also with the MPI standard continuously, the MPI 3, MPI 4. And now we have more than 3,275 organizations in 90 countries. These are registered organizations with our site. They are using it. And just from our website, we have crossed like a 1.61 million downloads just from our website. Of course, MVAPICH is a part of the Red Hat, SUSE, OpenHPC, SPAC. We don't keep track of those downloads. And also, it is not only just the count, but we have been enabling a lot of this top 500 systems all over the world. This just shows like a very simple download statistics. As you can see, we are in a very upward ramp over the years with different releases. So now if you open up our software architecture, this is how we look. I mean, below we see these are our support for all the modern networking technologies. So whenever some networking technologies comes, we look for the features, the mechanisms, and these are the research topics our students and staff work on. And same thing happens also on the multi-many core architecture. So this intermediate layer, so this is where we work on. And top we have MPI, PGAS, hybrid MPI, PGAS. And through that interface, actually, traditionally we supported HPC. Now we are supporting all the ML, DL, DASC. You heard about that talk yesterday. And the next thing is actually coming big data. I'll show you. Like we are running Spark over MPI, Spark over MVAPICH too. So we want to move all the big data stacks also with the MPI. And as we do the research, and once we publish the papers, I think Hari presented this yesterday, we go through a very rigorous testing environment within our group. We have almost like 200 servers continuously doing QA testing. So we have several full-time staff people. As you can see, like even every commit, we almost spend like 80,000 hours, core hours to go through all kinds of testing. So we want to make sure that the code which we release are really stable, and then that can be used on the other systems. So we have a lot of different versions of MVAPICH 2. I'll introduce them, and we are trying to unify. I know for the last several MOOCs we have been telling that, but it's coming. Okay. So I think Adam must be knowing. Adam, you will see in a few weeks there will be a new release. Okay, trying to combine all these things. It is already working. We just have to take through tests. So I'll just go through some of these and then give an overview. So I'll start with MVAPICH 2.3 series. I think that have been running. That is our production version. So we just made a release of 2.3.7 in March. There are a lot of features here. We supported Rockports. We provided Cray Slingshot 10, and then some blocking, non-blocking support, etc. So let me just highlight a few of these things. Of course, performance is important. I mean, we always work on the best internode performance. Collective offload using Mellanox SARP, and of course we are working very closely with Professor Samir Sande here on the close tight integration of tau for the profiling, so that you know where the time is being spent and we can optimize. And then we enabled, especially with the 2.3.7 release, the broadcast adapter, Rockport, and Slingshot 10. Okay, so let me go into some sample numbers. So this is the very latest numbers from AMD Milan SDR 200. So these are like the top kind of systems, very widely being deployed at many places. And here you can see within the node, we are able to go almost like 180 nanoseconds from core to core when we are trying to do the MPI level communication within the socket. And then this is the SDR 200. And the latency wise here you can see like I believe this is 1.8 microsecond. Okay, and this is like either on the local or even the cloud. I think Jitin will talk some of these numbers later on today. Even on the cloud, similar kind of instances, we have seen these numbers. And also the bandwidth, also we get very good intra-node and inter-node. Now, some of you must be knowing about the SARP, that is like the Mellanox in-network computing support. And we have been doing very tight integration with SARP. And these numbers, it's a little bit old, but this is the largest number we have taken on the TAC Advanced Computing Center. So you can see here, number of nodes, almost 8,000. This is the largest run we have done with MVAPICH 2. So this is, we have an MVAPICH 2X, that is an advanced version, and then we have the SARP. Now you can see with the SARP support, the collective performance really improves significantly because it is happening in the network, and we have done a tight integration. you can get an improvement of 9x, 5x, 6x kind of things. Now, obviously, with all these people talking about DPU support, there is a lot of focus, increasing focus on non-blocking collectives. Most of you know like the blocking collective. So when you are calling, let's say all to all, all the processes are not able to make progress. But if you do I all to all, there's a lot of potential for offloading it to either to the network or to the DPU. So we have been gradually focusing on improving that. So here you saw like the I barrier compared to the previous version. The green one is the latest 237. And as you saw, see in the slides, like we have the overall time and percentage overlap. So we are able to reduce the actual time from, you can see the almost 4.4x, and then increasing the overlap. Okay, so you need both. We want to reduce the latency and increase the overlap so that when the processors are operating on their execution time, the network is trying to do the collective. So if you can do the overlap, you'll get the best performance. So this is like the I barrier and I all reduce. Now this one is the tau. We have been working almost last 5 years. I was looking at the slide today morning, Samir. We had the best paper at Euro MPI 2017. And since then, we have been every release. I think we always work very closely with tau. And we have a lot of instrumentation within things. And we have completely supported all the MPI 3 PVAR, CVAR. If some of you are familiar, like we are able to extract the performance variables exposed to tau. Tau can do the analysis and then exactly tell the MPI library what to do. Okay, so we call it like just the personalized medicine. We are heading into that kind of a concept, personalized MPI library through the tight integration of MVAPICH and tau. So any center, if you want to run on a given kind of a cluster, we can optimize very well. Or even for a given application on a given system, we can use this framework. So it will you will do some sample runs, tau will do the analysis, and based on that analysis, we can drive control variables to the MPI. So the successive runs, a lot of parameters will almost get adjusted. So Samir will be talking more about that in the later part of this talk. So these are some of the new network adapters we have supported. So this is the Broadcom Rocky. So here we see these are very latest numbers on the 237. We get around like a 3.88 microsecond internode latency, and then the bandwidth wise, these are like the Broadcom 100 gigi. So we get around like a 12.17 megabytes per second unidirectional and 24.3 bidirectional. And then the Rockport network, this also we supported. This is a little bit different network. They call it like a switchlet network, but it has an InfiniBand plus an FPGA kind of things trying to do. So here we get around like around 3 microsecond latency for small messages and around 10.2 gigabytes per second unidirectional and 20.1 gigabytes per second bidirectional. And then since our stack supports Rocky, so we started enabling the slingshot. That means you see the slingshot, a lot of deployments coming. So we first enabled on the slingshot 10. That is the kind of Rocky compatible. And here we have done some evaluations. Access to these machines for the last several months have been hard. It has been very closed. But as soon as we started getting access, we have started doing some of these evaluations. So here it shows the MVAPICH2X, OpenMPI, and CRAMPitch. So that is the kind of the performance here, and then some of these are collectives. And then we are doing very, very well here. If you see this number again, MVAPICH2X 2.3, this is the intra-node in 220 microsecond, we are able to communicate. And then in the inter-node, here we are around like a 2.55, and collectives we are winning very well. And Quathar actually will be presenting later a short talk, and some of these numbers will be explained more. So that is the 2.3 series, and 2.3 series, if some of you remember, when we started working on the verbs, and we have been maintaining that verbs layer. Okay, but now the field is changing. So this is where we are trying to adapt. So this is where the 3.0 was introduced. So here, we are trying to go. If some of you are familiar, like the MPitch, they've been talking about CH4. Our 237 was based on CH3. So CH4 design, and now we have enabled both OFI, which is the Open Fabrics, libfabrics, and also UCX. So through those support, you should be able to now get able to run it over many of these systems, and this is how we are being enabled to enable like a Cray Slingshot 11. That's the network which is running on the #1 system. Also on the kernel is Intel PSM3, and also you can go through the UCX over InfiniBand. So now there are no more restrictions. Any network we should be able to support. And this is an alpha release. We'll be gradually adding more and more features. So what I'll just try to show some of the basic numbers for Slingshot 11 and OPX over OmniPath, and support for the UEFI and UCX. So these are some very common thing. It is there in our user guide. You should be able to configure either with a device CH4 UEFI or CH4 UCX, and then there are some of these variables you can actually select depending on where you want to do. So currently in this 3.0 release, we are just exploiting the CH4 point-to-point. We have our all old collective design because we have invested quite a lot over the last 20 years on optimizing our collective, so we are keeping those. So we are not throwing those away. So we have those collectives, and then we are including that with the UCX point-to-point or the UEFI point-to-point. So now let's take a look at this is the very latest Slingshot 11. That's the system which is the running again on the #1 system. There are few systems in Livermore and Oak Ridge. If you have access to any of these, you can run. We are getting 2 microseconds. That is very good on the Slingshot 11 internode with the switch for small messages. And the hosts are again in the AMD Milan. I think most of the recent systems are using this AMD Milan, so you will see a lot of numbers with that. Again, Quathar will be presenting more on that. And the bandwidth wise, here you can see like we are getting almost like a 24 megabytes per second, or 25 you can say times 8, so 200 gigabits per second internode, and bidirectional we are able to get 400 gigi. So this is the kernel-less network. We heard a talk from Dennis yesterday, and I think Doug will be presenting something tomorrow. So these are again early performance results, just like the few days back. We've been to run all these things. So what we are trying to show, of course, the hardware is OmniPath, so you can actually use the 2.37 with PSM2 that has been running. But now we have the 3.0, so that's what we are trying to show this difference. So you can see like the CH4 kind of tries to cut down some of the overheads in the number of instructions. I think Dennis mentioned that yesterday. So you can see direct impact here. It's not a big thing, but still you get like a 1.22 to 1.8 microsecond. This is like the overall latency bandwidth we see, little bit or more, but the biggest improvement you see in the message rate. I think that is one of the objective of the CH4 design, because you are trying to cut down on the cost, especially for short messages. You should be able to really inject messages. So here you see almost compared to this is a 4 ppn number, this is an 8 ppn. We are able to improve the message rate by 1.59 or 1.69. So that means if your workload is really small message intensive, you will be able to get a big boost with our 3.0 things. And this one is again with the 3.0, what we are trying to show again on that AMD Milan and SDR platform. If you use our 3.0, we are able to save some, not a big manner, some amount of latency, bandwidth. You push the bandwidth and reduce the latency, and that will be our next line to move forward. So while going on, so again I said this is like an alpha release. So we have been heading towards making our own CH4 netmod. That will take some time. Currently we are using the CH4 netmod from Argonne, but we'll try to bring all our earlier designs into point-point shared memory, everything there, so that we can have a good CH4 design. And as of now, the 3.0 doesn't have GPU support, but it's being worked on. So that will be our new design, that advanced version, Quathar and a lot of people have been working on. We have to test it. And then I think if some of you remember, like we have an MPI run RSH job launcher. We designed it almost 10, 15 years back. But gradually that is getting outdated. So we need to do a refresh. So because the technology has changed, all these networks have changed. So we are thinking of a newer launcher design, so that because as the system sizes are scaling, we should be able to even provide very good job startup time. So then let's move to the MVAPICH to J. I think Amir presented this yesterday. So this is the Java binding. And especially this is geared towards like this, all this big data stack. We'll talk about that a little bit later. But if you have the Java, so we created an MVAPICH Java binding version. Okay, so if you have any Java workload, you should be able to utilize our stack and then get good performance. And this is just trying to show a little bit of high-level things. This was presented yesterday by Amit, but he will go into more details tomorrow. So our objective is to really, all these big data stack, especially it is Spark and Hadoop and all, they focus on Java. And of course, people have done native design, including our group. Like we had native Hadoop over InfiniBand, like RDMA Hadoop, RDMA Spark. But then what happens, every time a network technology changes, you need to redo the design. It is very painful. On the other hand, if you think of MPI library, it is a portable library. I mean, most of the systems you have MPI library. So why go to directly to the network, instead come to the MPI layer, so that then it is portable. So that is our objective. So that's how we have enabled the MPI Java binding. So currently we have actually getting very good numbers on the Spark over MPI. Here it shows some like a basic micro benchmarks number, like the MVAPICH JRAs, MVAPICH JBuffer. We also have it can run also with the OpenMPI Java bindings. So now moving forward, so our MVAPICH X, which is the advanced version, that has a lot of support. So here is the like a derived data type support, because a lot of scientific applications use this derived data type. So we have been continuously trying to optimize that for both CPUs and GPUs. And we also have like the tag matching. That is also a big issue when this you are trying to do large scale systems. We have actually tag matching designs. Here you can see, like, if you enable the tag matching compared to the basic design, you should be able to get like a 1.6, 1.8x improvement. And so then we are also like not only trying to support the on-premise systems. As you know, a lot of people are moving into the cloud, so we want to make sure that the MVAPICH is also enabled in the cloud. So here what we have done, we are working with all the three major cloud providers, the Azure, AWS, and Oracle Cloud. Azure, I think Jitin will give a talk today afternoon, he's scheduled. So for AWS, we actually made a new release. AWS, as some of you know, they have a different network adapter called EFA. Azure uses direct InfiniBand. So whatever MVAPICH has InfiniBand, it will directly run there with some minor optimization and tuning. But EFA is a totally new adapter. So we have been working with a native design of our MVAPICH library with EFA. Nobody else, no other MPI stack has that. Everybody else goes through OFI provider. Okay, but we have done a detailed, in-depth design, and that gives us good performance, okay, compared to other libraries. So here I'm just trying to show the MVAPICH these are like on their latest ARM instances. Of course, the absolute numbers are not good. I think the community knows. EFA adapters are not as high performance compared to InfiniBand adapter, but compared to other MPI libraries, we are able to deliver better performance because we go directly to the EFA adapter. Okay? So then similar kind of things there, AMD on the AWS x86 instances. So we are trying to support both the x86 as well as their ARM instances. And Sule, who is working, he has a poster. So he has much more details there. So please feel free to discuss with him on that. And then the Oracle Cloud, so that is the third cloud providers we are working on. They are broadly working on Rocky. Okay, so since our MVAPICH library runs on Rocky, it directly runs on this. So this is how we are trying to target all the three cloud providers. And here there are some comparison with different libraries for some collectives and all. So there is a blog posted by Oracle Cloud. You can see more details there. So those are on the host side. So let me quickly move to the GPU. This version we have been working for many years. We made a very recent release in the GDR237. There's a lot of features here. But just to talk a little bit of this, I think most of you might be familiar with CUDA-aware MPI. If not, I mean, we introduced this concept together with Mellanox and NVIDIA at that time. They were separate people, but now they are together. So the idea is that if you have some data on the GPU buffer, instead of the user trying to do a CUDA mem copy and then trying to do an MPI send and MPI receive, can you do a directly MPI send from a device buffer? So that is kind of the early days of GPU direct RDMA. We introduced that at the ISC 11 papers. But now in the 11 years, a lot of other MPI libraries and stacks have adopted this CUDA over MPI. So, but now the question is like as you have this CUDA over MPI, because you are trying to move data from GPU to GPU, a topology and all those things matter. Okay, so this is what we have been optimizing. So this was like the data types again. As you can see, like we can improve by a factor of 15, factor of 3, depending on, this was a little bit older Cray CS term system. But this is something very latest what we have done with UMR. So we have taken the UMR concept and then trying to exploit or extract higher performance for the derived data type processing. And so this is a paper which just presented last week at the Hot Interconnect. So Kaushik will be presenting this tomorrow in more detail. So you can see here what we are trying to do. There are some different DDD bench milk here or NAS MGY. We are comparing the MVAPICH to GDR next. That is not like released. Compared to the current version, we are able to improve by almost 32%. And of course, we are comparing with other libraries also. Now, this one we have been focusing quite a lot recently. I think you might have seen some of this earlier, the compression, okay, on-the-fly compression. So think of like the GPUs, we put the data there and we trying to perform the computation. Earlier, we accelerated the communication. Now we are going one step further, okay? Because sometimes this, before you send, let's say you have a huge data, sending the data, even if you use the CUDA-aware concept, it takes some time to move from one GPU to the other GPU. So the idea is that, before sending it, can I do compression? Because I have a lot of GPU cores available. Can I do on-the-fly compression? And the other side, I do decompression, okay? So that now my message sizes has reduced and I should be able to get better bandwidth, latency and bandwidth. And that's what we have done. This was a best paper finalist in May 2021 last year. And then now we have enabled it actually. In the latest 237, it is available. You can turn on these flags on the fly compression and you should be able to see. Here are some numbers like AWP ODC. This is a seismic earthquake simulation. So here we have been able to improve the, like, as you can see, the flops 18% higher and 35% higher. And then the runtime also you get a reduction. And that concept now you can try to do in a multiple stages. So first we enabled it for point-to-point, but then as you know, the collectives typically sit on point-to-point, so they can take advantage of it. But now we have gone one step further. We have actually tried to do the collective design themselves with compression, okay? Because sometimes for point-to-point, you will be doing multiple compression, decompression, okay? Because I send it to you, you are trying to combine and again sending. Okay, so we have come up with a new set of all-to-all designs here. So this was like presented at ISC 2 months back. And again, here you can see the all-to-all runtime, whether it's a DL workload framework like a deep speed or a scientific PSDNS, we are able to give that benefits. So if you have any of the GPU clusters, I'll strongly recommend you to use this compression, on-the-fly compression feature, and you will be able to get good performance. And then, of course, these new kinds of systems are coming. You know, the DGX2 or NVIDIA is going for a lot of multi-rail environments. So this is where a lot of effort is needed to tune the collectives. And that's what we have been working on. So these are some of the DGX2 A100 systems. All the collectives compared to nickel, we are trying to show how much benefits you can get for small messages, large messages. And in addition to all-to-all, of course, as some of you know, all-to-all V is also important. A lot of scientific applications use all-to-all V, and that's what we are trying to optimize here. And this paper was presented at SCW workshop in conjunction with IPDPS. And that design is already available in the MVAPICH to GDR. So here we worked with the Hefty. I think Alan will be presenting some of the performance numbers. We have been working with their group. They have been designing this Hefty. So here you can see like we can give you performance like almost 5x or even 28x. And also we have done this, the upper graphs are showing the all-to-all latency on one node or 16 nodes, how we can improve these things. So then this is even the MVAPICH GDR, because the GDR design, earlier I said on the AMD GPUs. So there again, this is with all the earlier numbers are with NVIDIA GPUs. We also support AMD GPUs because that is being used now on the Frontier and other systems. So we have support for that. Here you see like a MVAPICH GDR. This is the 236. But similar features are there on the 237. We are able to get around like a 1.75 microseconds. These are collectives. As you can see, like some of the compared to OpenMPI, we perform very flat. So that gives good performance. And then this is the MVAPICH GDR on the Slingshot 10 with the GPU. So we can actually support even the CUDA-aware concept with Slingshot 10. We don't have the design with Slingshot 11 yet, but that's what is being worked out. But with Slingshot 10, you can see like a GPU to GPU, we are able to give like a 4.28 microsecond on the Slingshot 10, and it's trying to show some collective numbers on the right-hand side. And as we are trying to target these HPC, yesterday Amir and Arpan gave the tutorial on high-performance deep learning. So that is how we are trying to enable. If you take a look at, if some of you are familiar with PyTorch or Horobot, TensorFlow, so there is this intermediate layer, Horobot or Torch distributed or deep speed. We have linked our MVAPICH library there. So the broad idea is that if you think of like a Horobot can directly work with Nickel, or it can also work with MPI. So we are enabling the MPI part because MPI library is already optimized. So then if we take care of the underlying networks for any system, any network, you get it almost for free. Okay, so you don't have to go through any other layer. So that's what we have done. You can do CPU-based training using MVAPICH or MVAPICH X, GPU-based training using MVAPICH GDR. So in the end, we are trying to bring the big data also. So in the end, you just need an MPI library. That's all. That is our real vision. So that is the Convergence software stack where we want to show that as long as you have a good MPI library on your system, you should be able to handle not only HPC, machine learning, deep learning, DAST, big data, or any combination of those in a workflow. Okay, so that is our vision. These are some of the numbers we see, like compared to Nickel, compared to our MVAPICH GDR on some of the GPU evaluation on the Lawrence Livermore. This is an application I think Arpan and Amir presented. We are working with some of the computational pathologists here. They have a real need because they have very large data sets which you cannot fit it in the memory. So here, when we started, they were running like this training on one node with one GPU 32 hours, and we reduced to 27 minutes. Okay, just in 3 to 4 months, we worked with them and then really tried to improve. In the beginning, they were very hopeless, saying every 32 hours they will do the training, they will find some mistakes and then retrain. But now we were like within half an hour they can get this done. Of course, it is based on more number of GPUs. So we brought the HPC to the computational pathologist here. And similar kind of things we are trying to do machine learning. This is the QML Amir again mentioned. This is based on our MVAPICH library. We have a MPI for QML release. And as you can see, for some of the common things, k-means, nearest neighbors, we are able to boost the performance compared to Nickel. Similar kind of things for the DAST. That was also presented yesterday. So that is also the field we are trying to go. And then you can see compared to IP over IP or UCX, we are able to give better performance with MPI for DAST. So these are again all public releases. People should be able to download and run it on the system. So moving forward, like we are trying to take that on-the-fly compression to other collectives, is Allgather, which is being worked on. And Arpan touched a little bit yesterday, and then he will give also a talk tomorrow. We are really going for a lot of this advanced model parallelism, hybrid parallelism, super subgraph parallelism. So we are trying to exploit those to really make the deep learning faster and faster on the GPU-enabled systems. So then let me touch a little bit about the OISU micro benchmarks. As you know, that also started with almost the day one of our MVAPICH library. As we have been pushing the MPI, we also put the micro benchmark. Okay, so that I remember before OMB, people didn't know how to really evaluate MPI level performance. People know how to evaluate the application level performance. Then IMB was there, trying to verify the correctness, validation. But how do we really determine the MPI, like how much MPI send is taking, how much MPI bcast is taking? So that's how the OMB started. And over the time, as newer and newer features are getting added, we have been continuously releasing this OMB. And just the OMB 6, we also provided the support for the Java binding and then the Python support. Here it just shows some instructions, like, and these are all available on the website. So at a Java level or a Python level, you should also be able to see how to evaluate the send performance, receive performance kind of things in an isolated manner. So this is how, like, we have provided a lot of extensions. Here you are seeing point-to-point collectives, vector collectives, all these things we have extended in the Java. This shows the bigger architecture kind of things. So this OMB for Python, as you can see, is sitting on top of MPI for Py and sitting in parallel to the C version of the OMB. So depending on where your programmers are, they should be able to use either the C side or also on the Python side. And this is trying to show. So this is the paper we just presented. As you can see, like this, the top row OMB for Python, it actually supports all the features. Okay, that's what we want to provide all the features. So then we are continuing with this compilation of best practices. If some of you would have looked at our website, we have a link called best practices, and this is for the community. We also add a lot of information. So let's say you have some application, particular application running on your system, and we have worked with you adjusting some parameter. You know, MPI library, within MPI library, these days there are almost 200 parameters you can tune. Okay, it is becoming like a modern car. You know, so many things to tune. And if you really want, and it requires effort because you have to do tuning, you have to, get the performance profiling, and then see where the time is being spent. Of course, the tau kind of environment helps. But in the end, if you know that, oh, I need to change these 5 parameters, we add that to our best practice page. So if you are running any such application, like let's say Milk, Neuron, you don't have to spend that time. You can just come to our website and then see what parameter needs to be adjusted. And you can also contribute. If you have run something on a given platform, we'll be very happy to add your things to our website with credit to you, so that everybody gets benefited. We don't want people to waste time. So let me move ahead and then try to finish. Some of these are upcoming features. So this is the Convergence Stack. People have been envisioning HPC, big data, deep learning, machine learning. I know over the last 10 years, a lot of talks have happened on these Converged software stacks, but actually we have the Converged software stack. Okay, people just talk, we deliver. Okay, so we have actually this Convergent software stack, just like using the MPI, not only HPC and machine learning. And big data, as I said earlier, we had the different versions, RDM-enabled Hadoop, RDM-enabled Spark. They give very good performance, but now we are trying to bring that into the MPI library. So as you can see here, just this is like a Spark stack. So instead of the JNI, so we directly call to the MPI library. And of course, in the beginning, we are supporting it with MVAPICH 2, but you can run it also on any other of your MPI library. That's the goal kind of things we want to show. And look at some numbers. So here, if you see, like this is a weak scaling evaluation. Some of you might be knowing, just like OMB, on our big data project also, we have a high BD benchmarks. Okay, we introduced just like OMB. So you can actually do benchmarking for your big data stack. So here we are comparing on the same hardware, IP over IB, our RDMA design, and then this is the MPI level design. Okay, so it's the same InfiniBand hardware. Either you go through IP over IB, that's what most of the stacks, Apache's stacks run. And then we had our RDMA Spark earlier. So that is running, and now you see the MPI, you still get far better performance. Okay, because the reason is like the MPI library continuously is being optimized on better and better, and it is very much well integrated with the underlying network. So that is our goal, so that if an MPI library is optimized, why again go and optimize all other stacks? So that's what we are seeing, like a 4.1x, 2.2x improvement. Similarly, this is a strong scaling numbers. And in fact, this will be presented at IEEE cluster just in 2 weeks. We have the paper accepted. It is not yet released. We are going through all the testing. might be in after the paper gets presented in 2 to 3 weeks, we'll be making a release of this. And so this is also the different like Intel high bench workload, similar kind of performance benefit we are seeing. In some cases, you may see, like for example, here, if you see the middle line is our RDMA Spark, we still get better performance. Might be, let's say in this case, you don't see. That's okay. It depends on the workload kind of things and what was optimized and what was not optimized kind of things. So then this is the MVAPICH2 advanced. So currently what is happening, we have the basic MVAPICH2, then we have this MVAPICH2 GDR, MVAPICH2X, let's say MVAPICH2 AWS. So now since we have moved to the CH4 design, combining this is a little bit easier using net mode approach. So that is where we have been trying to reach that stage, but we have not reached. But this is where, as we move forward in a few months, we'll have a basic MVAPICH2 version, there is an MVAPICH2 advanced version, that's all. Okay, we will have only two different things. So advanced version will have a lot of all these features, and it will be able to support all the other networks. So then what is happening, this is a totally new project. So as you can see, like especially if some of you are running all these tests, let's say a lot of you are techies, so you actually log on, let's say OEC cluster or something, you log on, but a lot of end scientists or people, they don't want to spend time. So we are trying to bring Alexa, Siri kind of things to HPC. Okay, so that is the conversational AI interface. Okay, so the whole idea is here. I'll just give you a very highlight. So if you see the state of the art, you go through keyboard, mouse, touchpad, etc. Instead of that, can you directly talk? If you're an end user, you have a cloud saying, okay, run GROMACS on AWS instance of 10 nodes with this MPI library. That's all you need to tell. Everything else is happening behind the scene. So we presented this paper at ISC 2022, just 2 months back. So through conversational AI, automatically things get launched. Okay. Of course, I mean, this will make all of us lazier, but that is a different story. Okay. But we want to advance the state of the art, because a lot of people really spending a lot of time on if some of you would have used cloud and all, I mean, right? I mean, there is a lot of things really need to work before you get the results, and we are trying to really make it very efficient. So we are looking for like a 2030, 2040 time frame kind of things, where everything, you don't have to use your laptop or anything. Just talk to your iPhone and your jobs are running behind the scene, or before sleeping, just tell that, yeah, run this tomorrow morning, and the results will be there. And then we'll try to process those and give those summaries to you. Okay. So that is the kind of things. Poya will talk about that tomorrow. But overall, if you see like this was like the roadmap and plans as we started, like the initial support for CS2 CS4 channel. We are trying to gradually upgrade those things. Might be by SC time frame. We'll have a very good optimized design for CS4, and then CS early 2023 we'll make the CS4 channel as the default. Then of course these are all the other newer features, Bluefield 2, Bluefield 3, those kind of things are coming. Okay, so with this, I'd like to thank all the sponsors, but more importantly, as you know, always whenever I give the talk, these are all my heroes. This project we have been working on 21 years. A lot of students, staffs, they have come, they have contributed, and if you take a closer look at some of these lists of names, these guys are sitting on top of many places in industry, national labs and all. So I tell again all the new students, if you work hard, your name will be there in this slide in 5 years down the road. Okay. So with this, I'll stop here, and I'll be happy to take your questions. We have a few minutes, and then we'll go for a coffee break. Are there any quick questions?
So I actually had a question for the audience. So the last thing that Dr. Panda mentioned was the conversational interface. Do you guys think that is useful? Do you think it is necessary? Is there a need for that? Would it overcomplicate things? So let's say compare the current generation and maybe your kids. So if I talk to the previous generation, like the older guys, they would say, no, I would never use this because I can never get it right. But if you look at the next generation, the kids, they are mostly kind of growing up with this kind of an interface. So do you think this would be useful going forward, or this is a wasted effort? People will probably not use it. I'm just curious to hear what this audience thinks.
We'd use it.
Yeah, we will use it. Okay. Okay. Anybody else?
So consider this the informal user survey.
Yeah, it's just like, the driving is moving to automated driving. So why not? I mean, all these HPC runs and everything, we automate that. And I'm sure, I mean, let's say OSC or any of these centers, just like you call a service center of, everything is automated these days, am I right? Press 1 for this, press 2 for this. So that's what kind of things can be done, so that you don't need a lot of dedicated center people to operators and all, or programmers. I don't know, the forward-facing user support you can cut down quite a lot.
Let me rephrase the question. So, will you be able to trust such systems like conversational AI? If you have this system, will you be able to trust it, and will you use it? Can we have a show of hand? Like just one. How many of you will use it?
Okay. Okay.
Okay. Great.
Yeah. So we'll design the system so that it will be trusted. Okay.
And what do you think? If it gives you more insights, will you use it now? If you you have an output or a log from your system, and it is giving you some insights, now will you change your answer? Now you are more likely to use it or not?
Yeah, Arpan is going to the next stage. He's like almost writing a paper. You will say, okay, I ran these experiments. These are the 5 cases. I found out issues. I have solutions. Go and write the paper. Right?
So I would like to add a comment to that. So it depends on what you can do to build your codes. Could you, for example, tell it to download the OSU micro benchmarks, configure it with MPICC in your path, run it, and show you the OSU latency numbers, and just
that is exactly what we are going for. So thankfully, community, for instance, Samir is leading the E4S effort. I think Greg is here from Livermore with SPAC. So those kind of tools really make it easier for us. So for instance, if somebody says, if I say that, hey, go download MVAPICH 237, install OMB, so I can use SPAC and E4S to do that, because a lot of the automation has happened in the backend. So we just need to kind of use that interfaces. So in a sense, we are hoping to build on top of, let's say, giants in the community who have done a lot of the automation hard work for us in the backend. So that is the goal. So let's say if somebody says, hey, I want to run OSU all-reduce with 2 nodes, 24 processes with MVAPICH 2 on Frontera. Please give me the results. So we would like to process that and give the output to the end user. So that is what we'd like to go for. So let's say if I ask a grad student to do that, they would do that just like that. But if I ask a very senior professor or a very senior person, they would they would have some, let's say, starting trouble, so to speak, to get all this done. So can we avoid that? So one of the side goals.
To be honest, I also think there's a lot of potential when it comes to accessibility into computation. Could you imagine the use case, for example, to allow, especially when it comes to visually impaired people? I think there certainly is a lot of potential. Could you imagine how, for example, how is someone, for example, who is blind, even contribute to the field? I think it's something that we can often give for granted.
That's a good point. We hadn't thought of how let's say how this would impact people with special abilities. That's a very good point. Something we need to think about.
Okay, so I think we'll go for a break now. Thanks a lot again. And as of now, I think Samir, to answer your INAM is running like this mode. That's what I think Poya can even show you in a demo. INAM contribute, you give commands, it runs INAM and shows you the things.
That would be very impressive.
Yes. So I think talk to him, might be later on, if people are interested, he can show a demo. Okay. So it is really going for a conversational AI. We have training done, everything, and it recognizes your voice. Might we will try with your voice and see whether it recognizes you or not. Okay. But what Hari said, that is the end goal, like what you said, like run OMB on MVAPICH2, on Frontera, on give me the results. That's what we want to achieve. Okay. So thanks a lot again. So let's take a break and, oh, sorry. Yeah, go ahead, Alan. Yeah.
What is MVAPICH team doing to tackle communication-bounded algorithms on upcoming supercomputers? For instance, most supercomputers target the top 500 list, so they are very good in arithmetic computations, but they are not very good in handling communication-bounded algorithms. For instance, the HPCG benchmark, the top one, their supercomputer just achieves 3% of their peak. So this is normally based on the performance for the network. Most MPI distributions, I think, don't help much on getting closer to the peak.
Yes.
So what's your team doing to handle that in the future?
Yeah, no, so that is a good question. So Alan is asking like how to like really push to get the best out of the network through the MPI library kind of thing. I mean, that is continuously we've been working on. I mean, so at some time we have done like just like you people and all, we have been talking because you people are like application people, we are interacting with you. But we are very open. I mean, at any place, if we want to, we have in the past, like I showed some AWP, ODC, those kind of things. Currently, we are working with a lot of deep learning application developers. So if you are seeing some bottlenecks, we'll be very happy to work with you to see. And that's where we have been developing this INAM. We are working with Tau so that we can actually show you where the time is being lost. And then once we know that, then we can optimize it further and then move.
So one thing I think Matt also mentioned this, hiding the communication would be essential. So can you overlap computation with communication? So if you look at vendors like NVIDIA, they are coming up with solutions where you can offload certain communications, but just offloading itself would not suffice. Some changes in the application would be required to see how you can hide the communication overhead. So Matt mentioned that researchers at Idaho National Labs are trying to restructure their communication to use more non-blocking operations. So let's say in your case, if you are using all-to-all, is it possible to identify, let's say, data independent compute, which can be done? So that could be one method to see if we can get more or let's say improved scaling.
Okay, thanks, Hari. So let's take a break. Otherwise, we don't want to get delayed. Today is a very busy day. We want to